Hello and welcome. I'm Shadow of Shadow Gaming, bringing you episode 26 of Programming with Shadow. In today's lesson, we're going to be looking at a new data structure, a queue. So a queue is, or to me, always felt similar to a stack. Let's go over the text here. The stack, you put something on and it does like this. Like let's say we put A on, and then we push B onto it. B takes the top spot, and A is no longer in the top. And if we do C, B, A, it goes like that. And if we get one off, like if we get the top one off, we pop it, we get C here, and these trade places. These trade places. That's a stack. The queue works slightly differently. So queue, let's put in A, and the keyword here instead of push is enqueue. So enqueue B, C, D. Notice we're putting them in order. That's important because the next thing you do is you dequeue or deck. And you would take off A, and B is now the top. Like that. And if we deck them off, we get the B, and then the D, E, and F, three places. So it's literally a queue, like if you're in a waiting line or something. That's exactly what's happening. You start from whoever got in the line first is who gets out of the line first. So a stack's known as the last in, first out data structure. A queue is a first in, first out data structure. So queues can be done with arrays or lists. You can create one of those as the backing data structure as well. There's some overhead though if you go that route. Problem is adding it's easy. You just keep adding to the list and adding. Or removing is a little harder because then you have to keep track of, you have to remove it and move everything up, or leave it and just have it keep growing. But usually you remove it and move everything up the list. That being said, looks like a really good time for another data structure as the backing data structure, the linked list we've looked at before. So the linked list, if we want to add one, we just start with, say we start with A, add one, we just add a new link, it becomes B, get one off, we remove it, and just make the other one the previous head. The linked list work well for or queue, so that's what we're going to implement here. Might do both, so we'll see. Let's go ahead and get into it. That's a queue. Let's go ahead and run this just to get it running. .NET run. Glad it doesn't WAP over my stuff. So I've disabled implicit using, so we have to do the system here. Let's create a class over here. We'll put it in file. Call it queue of linked list .txt. Let's do this. So public class queue with linked list. So this is another one of them that we're implementing it ourselves here, but text. We're implementing it ourselves, but we have the ability to. There's one of them built in. There you go. Hello world ran. We're not going to make use of the built-in queue. We're going to implement our own first, and then we'll back to it. But we are going to make use of the built-in linked listable. Let's just go ahead and do that. We'll do We'll add a variable here for it. So private linked list of t items equals new. We're gonna have to add system.collections generic. We need to make this a t. There we go. So there's just our backing data structure. So this is the systems collection generic linked list of t. So let's go ahead and make use of that. So first thing we want to do is let's add a count method, I guess. It's usually nice. Already got it built in. So let's do the enqueue method. So this is pretty easy. So enqueue the item. So items dot add last item. So very easy. We just add it to the last item on the items. We already started with new up here, so it's being created to begin with. So I actually don't know what count is. So C# linked list, see what count property is. I'm assuming it's constant, but let's make sure I'm not on that. Yeah, retrieving this value is a big O of 1. And you can find that in the documentation. And add last is big O of 1 as well. It's constant time as well. So let's do the dequeue deck. I've heard it both ways. I'm actually not sure. I would do it dequeue, but maybe either way. I'm not sure. So let's do let's do if items dot count equals 0, throw new invalid. We'll do invalid operation, I think. All right, so otherwise we can do t value equals items dot first dot value. Possibly null. Okay, so we were actually checking here that it's not null, right? We know that items is not null. First is the first list, and it may be null, but there's more than 0 items. Maybe we could check that. I think we're going to use a different one, though. We're going to use the exclamation point. So this is known as the null forgiveness operator. This basically means we're saying, okay, we don't believe this is going to be null, and I think this. We're saying this won't be null, so we should have a value. Now we need to remove it. We have a remove first, which is big O of 1. Probably see that in the list if I check. Probably should check. So just a second. So add first and is add last. That was last. And remove. Remove first is big O of 1. Add last is big O of 1. Add first is also big O of 1. So good. So they're doing what we expect. Remove last is also big O of 1. Okay, so keep track of the references, which is good. So that means we've got a method here, and I guess we need to return. return value. There we go. So here we're checking if it's null, if it's 0, if there's nothing on it, we throw an exception. Otherwise, we get the value, constant time. We remove the first, constant time, and we return constant time. So this method is big O of 1 as well. This here. Make it easier to find in a minute. We can do that if we like, since it's one line. Alright, so that was very easy. So there's not there, so compared to some of the what we've been doing recently with the console, this is actually pretty easy. We're just doing basic linked list operations. Let's add another one. Let's add a public t peak. Peak if we're going to do the exact thing. We'll just copy that. Then we'll do return items dot first dot value. So once again, this is big O of 1. Checking for the exceptions, big O of 1. So we have another big O of 1 method. We'll do it clear as well. Let's do it clear. While I'm looking, clear is big O of n, where n is count. So it has to clear everything. We'll do public void clear. All it does is call items.clear. Big O of n. So there's just a big O of n operation. That means it has to operate on the entire linked list, no matter how big it is. I think that's pretty much the queue. Could do one more method here. Public bool is empty. And we can say items.count equals 0. There we go. We've got one more method, and this is a property. I said method, but this is a property. Big O of 1, because count is. There we go. We've got a nice clean interface here, and everything big O of 1 except clear. Let's make use of this. So if we go over to program.cs, let's clear this out. We'll do queue of linked list, and we'll just put integers on it. Something like this. So now let's add some values. So, well, let's do strings. We'll just do like we did before, actually. Queue of linked list dot enqueue. And in some languages like Python, this will actually, it'll use, I think it uses, not using Q2 as well, actually. I was going to say, I think it uses push and pop as well, but I'm not using. But either way, it's the concept of adding something to a queue. We'll add an A, add a B, and we'll add a C. Let's go over here. Let's add one more method. One more. Let's do a display. Override string. Comes dot string. See if this doesn't work. I think items is not null. Yeah, we can make it read only. I think we're good here. Yeah. Well, let's see. So let's do Q with linked list dot to string. This one. So let's see what this does. So if we run this, I think we should see this, and we may have to customize that to string method or add our own display method. Yeah, let's go custom. Do this. Let's do string.join items. We'll just do that. So Q, I'm pretty sure we're about to find out, but I'm pretty sure Q enters I or implements I enumerable. Doesn't show off the docu. If you're in another IDE like Rider or Visual Studio, it'll actually tell you what it implements. It does. It implements I collection of T and I enumerable of T. So good. All right. So there we go. So here's us a display. So let's go ahead and do some more. Let's do a peek. Value console.writeLine. Something like this. And we'll just put the value there. So, and then we'll print it out again and we'll see that it didn't override anything. Then if we pop or deck or Q with linked list there, we'll do that. We'll copy these two, we'll print the 2 lines. Something like that. And we should see the A has now fallen off the list. There we go. So it looks like it works. It works just like we were hoping. So good. There's just a very quick Q. So that's an implementation with a linked list, and you can see it's pretty easy and everything's constant time except clear here. We can also do it with a list of T, just like we did before. Like I said, it takes a little more work on the deck you make. Let's go ahead and make another one just to show the example. We'll do Q with list.cs. So this is a list of T instead of a linked list of T. Q with list. So it is a private read-only list of T. We need a T here. Items equals U. This one can be a collection expression because it's a list. So count is the same, public int count items.count. As we've looked at before, this one is big O of 1. Public void in Q. In Q's easy. Notice it's easy on both of them. Well, on stacks it tended to be a little harder. On Q it's easier, and Q's easy, harder. That's the last in first out. Last in first out, or first in first out. Items.add item. And there we go. We added it to the list. Big O of 1. Unless the list has to increase size, I think. Let's see what the docu actually says for that. So I think it's maybe amortized as big O of 1. Yeah, if the count's less than the capacity, it's big O of 1. So I guess we have to say it's big O of n, though. So here it's usually better, but not all the time. So let's go ahead and do a decu. This one gets a little more difficult. Here, I'm going to go back over to this and grab this. We'll throw the same exception here. So t value, this will look very similar. Remove at 0. So this is where you start getting inefficient at. So we look up remove at for a list, it's not going to do it. It's not going to fare as well. So what it has to do is it has to remove the item at that index and then move all the other indices up. This is a method, is big O of n, where it is count minus index. So we're at that point, it's no longer we are now doing better on the linked list than we are the this one. Than we are the list. So if we do big O of n here, there's just two big O of n methods. Not all bad though. So if we do public t peak, do that again. It is just return item at position 0. This one is constant, and this is even quicker than the linked list bud in general. I guess it won't be much though. It's basically direct access versus a one layer of indirection, so not going to be anything significant, but not bad. And see, let's check clear while I'm checking everything. If you go look up clear, it big O of n just like before. Void clear. So little worse. We also did an empty, I believe. Public pool is empty. There we go. So there, I think we got relatively matching implementations. And I guess we need to do a public toString. String, and we'll just do the same thing. We'll do a string.join. All right, so there we have us a copy. So what we're going to do now is we're just going to take all this. I'm going to paste it here. We're going to add one line here. We're going to do console.write line cute. Let's copy that and let's make this one a linked list. Here we'll just let's do this. So I'm going to select my text here. I'm going to press Control D a couple times to select all of these. We're going to do back to get to the front, and we're just going to do this and remove. And we can remove the bars here just to get this happy. So there we go. So we should see it as far as what these two runs look like, they should look the same. And what do you know? Looks exactly the same, which is good because it should be the same implementation, just different way of implementing. There we go. That's a queue in a nutshell. Um, I've actually used depends on what you're doing, but I've actually used stacks a whole lot more than queues just in general. I would guess if you're doing more on maybe a network side, you would see queues a whole lot more than stacks though. Depends on what you're doing. We still got a bit of time, so let's do one more. Let's do copy this one more time. View of system import. This one, let's just do it like this. We'll do queue of string queue equals new. Oh. We'll just select these just like before Control D a couple times. There's probably an easier way to do this, but we'll just replace it. And there we go. We've implemented the same thing with system. Notice we use the same methods and everything. So the one thing here is I think the toString is not going to work. So let's run it and see. We may have to make an adjustment. Yeah. So there's two ways we could do it. We can just write our own method here to take the queue and or just do the exact same thing we're doing here. Let's override it because why not? We have time. Something like that. This would probably be what I would recommend in general. So this would be, we're making our own more, we're making our own more concrete queue here, but in this example, we're not really going to do much. We're just going to do we'll just do this, and we'll say yes, we'll do to array. To array. Can't do that. Let's do it like this. String.join base.toArray. And we need to add the parentheses. There we go. Let's see if this doesn't just work. I'm not 100% sure if it will or not, but we'll see. So let's see if this just works off that easily. Yeah, okay, good. So that was something I actually didn't think of trying before, but since we had time, it was like good enough to try. So what we did there, we just implemented or inherited from Q of T, and we did our own custom thing to it. So you could use this something like this as a way to make your own class here on Q. And your Q here just so happens to be more specific than what theirs did. So theirs gave us a different. It tells us it's a queue. We overrode it here, so that we do our display here. We can see the content. So that's just making use of inheritance. And if we needed to do more things, like say we wanted to change the, I don't know, say we wanted to change the count so that it did something else, we could do that. If we wanted to change the deque or the deck or the deque or enqueue or peak, we could adjust them. That's how you can make a queue or a stack, for example, for that instance, make them more specific to your use case if you need to. So that's pretty much all we're going to cover with this with a queue today. Directives unnecessary because we overloaded it instead. I don't know why it's doing that. It's like it won't let me get up to the top. Yeah. I've never seen it do that. That's odd. I don't like whatever it's doing. There we go. It's like it's not letting me up there to them. I don't know why. I've never seen that before. Sticky scroll. I've never seen that. Well, now I've lost it, so I guess I won't. I don't know how I enabled that, but apparently that's something you can do. Oh well, we won't worry about that. But yeah, so that's queues. So queues are just a really simple data structure, known as first in, first out, meaning the first item you put into a queue becomes the last item or the first item to come out as well. There's exceptions to that. You can have what's known as a priority queue. That means each item has priority, and then stuff with higher priority gets out first. We may look at that in the future. I'll say it's actually easier to implement with another data structure instead of a queue, but we might look into that. So what we did today, we just looked at what makes a queue. We did 3 different implementations here. We did a linked list, and we've seen linked list is probably the most efficient, but there's some maybes to that. The methods of a queue, we have a count, we have an enqueue, a dequeue, or deck. I think it's dequeue personally, but we have a peek, we have a clear, we have an is empty, and I did a toString to make it easier to see. Everything except clear for linked list is big O of 1. Everything's constant. All the linked list operations are fast relatively for large sizes. List, we did the same thing but implemented it with a list of t backing. The enqueue and dequeue are both big O of n. Peaks constant, but count here is constant as well. In general, it's slightly less efficient. The third one here, we just inherited from queue and we overrode its toString method to give us a display. So system has a queue as well, system collections.generic.queue. And it works very similarly to what we implemented in these classes. So in general, this is the recommendation is you do something like this and then implement whatever you need. We've seen here that all the operations were they do what you expect. You enqueue to put something onto a queue, you dequeue to pull it back out. I think if you look at the queue class itself here, I believe there's a try and queue and maybe even try peek. I guess that wouldn't make sense. I guess it might though. You would return maybe a bool and do that. Bool if it was successful, and if it did, you got null. If not, you didn't get something like that. But you could implement something like that if you needed it as well. But that's queues, so not really that complex. Text. So that brings us to the end of the initial data structure. So these are what I consider to be the basic data structures. So I think we'll plan for at least one more lesson that actually builds up something with a queue. What I'm thinking is do like maybe a waiting line queue simulation. I think we could do that. I think we have almost everything we need. That puts us one lesson out though, so that'll be lesson. This is 26. That would be lesson 28, because in the middle we need to look at a randomness. So in C# randomness is done through the system.random class. So that may be where we actually look at next is mess around with generating random numbers in C#. I don't think we've done that yet, so that'll very likely be the next lesson, and then we'll look at implementing a queue with it. So that's going to do it for the day. So that's been your queues. So thanks for watching. Have a wonderful day.